So last time we talked about linear models. Those are the real world problems we encountered, and they turn out to be described by linear differential equations that can be solved completely. There are different types of problems we talk about. We talk about population. We talk about isotope decays. We talk about circuits, mixture problems, and all types of problems. But most of the time, the problem would be nonlinear instead of linear. Linear is just a simplification of the real situations in many cases. So then we have to deal with nonlinear differential equations. For example, when we talk about the population, okay, we would consider, different factors affecting the growth of population. And then we have logistic equation or logistic model and some other models. And we especially include competition between individuals in the population. Okay, so let's just start from population dynamics in this section. So we're going to define a relative or specific growth rate, which is the rate of change of population dp over dt divided by the population itself. Okay. So the relative growth rate is just growth rate divided by the population itself. So it tells you the percentage, right? Yeah. What percentage is the population growth or decay or decreases? So that would be a function of population P itself. Obviously, at different population, you will have different relative growth rate. So this definition can be rewritten as dp over dt equals p times f of p. Okay, so that's completely from the definition of the relative growth rate. So then, this fp can be different functions depending on situations. In the simplest case, we already discussed in 3.1 when f of p is a constant, and we already solved this problem in the first section. So then the next model, when we consider more realistic situations, it's called the logistic equation, where f of p is a linear function of p instead of constant. So it will be a minus bp. So that's called a logistic equation. So you have different factors affecting the growth of population. So the constants a and b are both positive, and a indicates the birth of the population, reproduction, okay, and b is a factor affecting the growth of population by competition. So it just has the negative effect for the growth of population. and it's proportional to P itself, okay, in this logistic equation for the second part. So then we get the differential equation dP over dt equals P times A minus BP. Okay, so this time we're trying to solve a nonlinear differential equation. That equation can be solved, completely analytically. So what do we do? We can convert this equation to be a separable equation. Okay. So what do you do? We can do a little simplification for the equation on the right hand side by factoring out the negative b, so that we have negative a or b plus b in the parentheses. Okay, so that will make the coefficient p inside the parentheses be 1. Okay, so you can easily check this equation, by distributing negative b on the right hand side, you get the original equation. And then what you do is divide by p and negative a over b plus p on both sides of the equation to get the dp over p times p minus a over b equals negative b dt. Okay. I have written p minus a over b to put p in the front. Okay. But that does not change the equation itself. Now, what you do, you can again use partial fraction decomposition. If you remember what we did before, or you learned in Math 112 maybe. The right hand side, the left hand side can be split into two fractions. When you have 1 over p times p minus a over b, it turns out that you can rewrite in that fraction as b over a times 1 over p minus a over b minus 1 over p times dp. I just missed the dp on the left side. Sorry about it. Again, the partial fraction decomposition says you can decompose a fraction based on the factors in the denominator. So we have two factors in the denominator, p and p minus a over b on the left hand side. So then you can split the whole thing into two fractions. All right, and you can figure out the constants associated with each part. Okay, and it turned out that this is what we get on the left hand side. You can easily double check it by combining the two fractions on the left hand side and simplify it. Okay, and then we can cancel b on both sides and multiply a. Okay, to get 1 over p minus a over b minus 1 over p dp equals negative a dt. And the reason we want to do that is now we can easily integrate on the two sides of the equation. Okay, so that's the whole point of partial fraction decomposition. We want to integrate. So then if you do that, you're going to get two natural logs on the left hand side, namely ln absolute p minus a over b minus ln absolute p. On the right hand side, you just get negative at plus arbitrary constant c1. Okay, we just use c1 to denote the arbitrary constant. And the left hand side have two natural logs that can be combined as the natural log of the quotient of absolute p minus a over b over p. Okay. So that also means if you take the exponential, natural exponential, which we have done so many times, to end up with p minus a over b over p, the absolute value of that equals e to the negative at plus c1, which is again e to the negative at times e to the c1. Remember, when you get the sum in the exponent, it ends up with two exponentials multiplying each other. So then if we want to get rid of the absolute value sign on the left, then you have to put a plus or negative on the right hand side. Okay, so you end up with two situations. So p minus a will be or p equals plus or minus e to the c1 times e to the negative at. But at the end, you only get one of those in any real world problems. Initial value problems, you only get either positive or negative. So we can call this arbitrary constant C2. Okay. So then we get P minus A over B equals P times C2 e to the negative at if we multiply P on both sides of the equation. And then we can do a little more simplification by moving around the terms. If you move the terms with P on the left-hand side and the constant A or B to the right side. Okay, so we get P minus P times C2 e to the negative at equals A or B. And then in that way, we can actually solve for P completely or explicitly. So factor out the P on the left-hand side, we get the P times 1 minus C2 e to the negative at equals A or B, and then you just divide by 1 minus C2 e to the negative at on both sides to find the P. So, so we got the solution for the differential equation P equals A or B over 1 minus C2 e to the negative at. Again, we need to determine this arbitrary constant C2, and that can be determined from the initial condition. Suppose initially the population is P0, then we plug in 0 for T and P0 for P to the solution and solve for C2. Okay, so once again, e to the negative a times 0 is just e to the 0, which is 1. So we get 1 minus C2 in the denominator on the right-hand side. And then we can solve for C2 by multiplying 1 minus C2 on both sides. So we got a P0 times 1 minus C2 equals A over B, and then you just divide it by P0 on both sides, and then solve for C2. Okay, so 1 minus C2 equals A over B times P0. So C2 is just 1 minus A over B P0. All right, if you move around C2 and A over B minus B over B P0. So eventually the solution to the initial value problem is just P equals A over B over 1 minus C2, which is 1 minus A over BP0 e to the negative at. And this can be further simplified a little bit by multiplying BP0 both on the top and at bottom to each term. Okay, remember you have to do that. Then the top just becomes AP0 if you cancel the B. All right, then multiply P0. So in the denominator, it just becomes BP0 minus BP0 minus A times e to the negative at. Or you can distribute the negative sign in the denominator in the second part to get the BP0 plus A minus BP0 e to the negative at. So that's the solution find a solution to the initial value problem. Okay. Yes.
So I understand the integration, but I don't understand where you pulled A over B from when in the fourth step up at the top and towards the right, right there.
Here.
Yeah.
Yeah. You have to. That's why we need to partial fraction decomposition. So you got the 1 over p times p minus 1 a or b. You can decompose it into 2 fractions, and then you just got the b over a, on the top of each fraction. So you use the 2 factors in denominator. You can write this fraction 1 over p times p minus a over b equal to a1 over p minus a over b minus a2 over p, and then you solve for a1, a2, it turns out just b over a. Okay, so you have to do that a little bit, but it's not complicated. Okay, I think we did it before, so you do it in the same way. Any other questions? Okay, so we got a solution for the problem, and then so one thing we want to know, what happens in the long run, what the situation, the population is. So if the t approaches infinity, the time, so then because a is positive, so negative at becomes negative, approaches the negative infinity. So e to the negative at just approaches 0, right? So at the end, the second part in the denominator just approaches 0. Then you only have a p0 over bp0. Then p0 is canceled. Then so p approaches 0 or b. So that tells you the stable population in the long run. So at the end, the population will be stabilized to a over b. All right, from this equation itself. Okay. So we just solve the problem, and we're going to stop here today. Let me just stop the recording.